Morning, everyone. Today, it's a great pleasure to introduce Didier Lesesvre from the University of Lille, who's going to kick things off and tell us about the relation between zeros and central values.
Thank you very much for the introduction, Tim, and thank you for the organizer to organizing this great conference in a perfect place. I'm very glad to talk about this topic. So that's the first time I will discuss this project. So it's a slide talk. I discussed that with many people, and I tried to do something a bit different with a lot of diagrams and colors to try to emphasize where I'm looking and what are the shape of the arguments while giving details. So you'll tell me if it works or not. So as I said, that's a recent project and a joint work which is still ongoing. Was hoping it was done for this week, but maybe it will last some more weeks with Chacha from Kyushu University. And more precisely, what will I talk about? So I'll give a brief introduction about the general problems of answering questions on average on families of automorphic forms. And then I'll discuss more precisely, for those not knowing automorphic form, it's perfectly fine. We'll mostly talk about L functions. And there are zeros and central values. And what I want to advertise is this connection between both. And we can deduce results on one of them from results on the other one. All that will be relying on an explicit formula that explains or rewrites central values in terms of other objects. And these other objects have to be understood on average. And these will be using three types of arguments or tools that I will present in details, that are more or less three huge sections of the talk, which are ranking bounds, studying moments and sums of coefficients by means of trace formulas, and controlling zeros, and more specifically low-lying zeros. That's all the content I will be addressing, taking a bit of time. So I start with an introduction, and I'm sorry in advance for those who already saw the next two slides. There's at least one person who saw them, but I believe it's a not so bad introduction for those not being used to automorphic representations. So in number theory at large, there are various types of objects. You may have met one of these. Elliptic curves, for instance. You can wonder about counting rational points or the structure of the group of points of elliptic curve. Modular forms that can be seen as generating function of certain arithmetic quantities. Mass forms that are eigenwaves on drums being arithmetically shaped. Or Galois representation, which are a main tool to study algebraic extension and algebraic number theory. All these objects, despite very important and very active areas, can be seen, at least conjecturally, as different faces of single object, which are automorphic representations. I won't be defining anything more than that for automorphic representations, but that's one of the motivations to study these objects. And of course, we can guess that the study won't be easy, because each of the objects I mentioned before, elliptic curves, Galois representation, are still pretty mysterious. So putting all of them in the same framework won't solve all the problems. And the solution will be to maybe be able to say something on average. That's exactly the same spirit as what we do when we count rational points or we seek primes. We don't know exactly where they are, but maybe we can say, up to a certain height or up to a certain point, we have that many, we have certain density, we have certain distributional results. And more specifically, in the setting I'm considering, not only for this talk, for a general group, we can define automorphic representations, which may relate to classical objects or not. And that's a huge set, so we can truncate it to a finite set by a notion of size. It will always be the analytic conductor, but it may be something else. That's basically the aspect we're considering, maybe the level, the weight, the spectral eigenvalue, etc. And then we can wonder all the classical questions we have in statistics about a finite set. What's its cardinality? There's a question of giving Weil laws. What's the distribution more precisely? does it equidistribute with respect to a certain measure? And the same question for associated objects. And that's over for automorphic representations now. I will be focusing on L functions and two important quantities, which are the zeros and certain values of these L functions. So to one of these automorphic representation, you can think modular forms, mass form, etc. You can associate an L function. So Matt gave a great lecture last week about L functions. We won't need to know that much. What we need to keep in mind is that an L function is basically defined as a Dirichlet series on a certain region where it converges, and also as a Euler product, so product of polynomials in e to the minus s, all that inverse. And it has a lot of good properties. So it can be meromorphically continued to the whole complex plane. It may have specific poles, etc. And it has a functional equation. So that can be seen as a generating function of pi, and often that carries a lot of information about the object itself. So now let's give a bit more detail about the setting I'm really talking about here, which are zeros and central values. So for both separately, let's discuss a bit. Zeros of L functions can carry a lot of information about the underlying object. So we can think about like prime numbers. Prime numbers, we have results like the prime number theorem that come from basically non-vanishing results or zero-free regions. Chebotarev density theorem more or less exploits the same ideas with the Dedekind zeta function and looking for specific vanishing or not. And even geodesics on the hyperbolic surfaces can be studied by looking at zeros of the Selberg zeta function, for instance. So understanding zero would probably bring a lot of consequences about objects that may be more difficult to study in them just by themselves. So how do we, one of the way we use to study zeros of L functions, to quantify how do they behave, how are they distributed, is this quantity that we'll be dealing with a lot and studying a lot. That's called the one-level density. So you take a smooth function, think of it as a Schwarz Bum function, phi, and you sum over all the zeros that I write as half plus I gamma pi, but I'm not assuming the Riemann hypothesis now, so gamma pi can be complex. So basically I'm summing phi of the zeros. And since phi is a Bum function, or essentially a Bum function that truncates the zero up to a certain size, and I put a tilde here that I'm not defining, but it's just a renormalization of the zeros so that the mean spacing is 1 between the zeros. So I'm truncating all of my zeros up to a certain support, and since they're evenly spaced, I'm selecting only zeros close to the real line. Gamma is close to zeros, that means we're close to typically 1/2. That's why we call that low-lying zeros. That will be giving statistics only on those zeros. And there's a lot of literature for the last 2+ decades about low-lying zeros. And the main driving force of this literature is this conjecture of Katz and Sornak that comes from the analogous setting in the case of function fields and of random matrix theory, where we understand what happens. And they translated that in the case of automorphic forms. So what the conjecture says in, high-level conjecture say, for any reasonable family, I don't discuss what that means, but basically families arising in practice, and any Schwarz function, we have that on average, that left quantity is that, so fx is always the truncation of the family as I defined earlier to a finite family. So on average, this family, when you let it grow, it behaves as something explicit. So this is an explicit measure with density Wg of phi. And Wg is not anything. It's in fact conjectured to be only one of the 5 possibilities that arise in the case of classical groups of random matrices, orthogonal group, unitary group, symplectic groups, etc. So these Wg are well known, and the conjecture says that, in fact, the zeros behave exactly in one of these 5, as one of these 5 classes and nothing more, despite the wide generality of the conjecture, like any family of any kind of automorphic or number theoretic objects. Okay, so this is particularly important to have for any Schwarz function, because imagine then, in practice, what you want is to know if an L function has a 0 or not. Does it vanish at 1/2, for instance? Then you would like to take phi to be the Dirac delta at 0, that quantifies the vanishing at 1/2 or not. Of course, you cannot for a Schwarz function, but you can approximate it pretty well for any Schwarz function. And then, well, you just plug that phi or approximated version of your Dirac mass on the right, and you have your answer, on average, at least on the family. So that's a pretty strong conjecture. Now, on the other side, we also carry about central values. So central values, the values at 1/2 or more generally the center of the functional equation, also carry a lot of information, rank of elliptic curve, automorphic periods via Watson formula, etc. So we want to understand how they behave, and there is also a conjecture about these L values. And the conjecture is due to Keating and Snaith, and says the following. So always for any reasonable family that we don't define, the logarithms of these values are expected to follow a normal law, so exactly just a standard normal law, with a specific mean, M, and a specific variance, V, and on, of course, on average. So, for instance, that started with Selberg's result that if you look at the zeta function and the value on the vertical line, the critical line, its logarithms are also distributed along a normal law with mean 0 and given variance. And the conjecture just generalizes that. Okay, so the aim of my talk today is to explain that well, these two results are connected, and basically we can deduce one from the other, or partially one from the other, and I'm explaining that now. So before giving a proper statement, because for now everything is blurry, this is the kind of statement that I want to advertise a bit, and that we understood with Chacha recently, is that for these reasonable families, if you know a result towards the Rudnick-Sarnak conjecture, that means so the result like that, but not for all Schwarz function. That's too strong. You could plug almost everything you wanted, but only for restricted Schwarz function with Fourier support supported in a certain segment. Then you can deduce a distributional statement towards the Keating-Snaith conjecture. Not an equality, sadly, but something close to the normal distribution. So that's an idea from Max Radziwill and Sound from last year. They did that for quadratic characters, or quadratic twists of a given elliptic curve. But the strategy is pretty general, and that's part of what I want to explain. So as I said, I discussed like that just in the next slide. We have this condition which is important, and we'll see that the support determines a lot the quality of this eta that we don't understand much. What we would like is to have eta equals to 1. For a lower bound, that's the best that we can hope for. And then we would be pretty close, at least from the lower side, to the conjecture. Okay, so now so this eta depends on the family, of course. In fact, the type of symmetry of the family, the WG appearing above, and the support of the Fourier transform of phi. And here's the dependence. So they're just an explicit eta FL, depending on F and L. We don't care much about well, the exact formulas for now. But what we notice is that if we have the density conjecture for any phi, allowing L to be infinity, any Fourier support, so pretty concentrated phi, then you cannot even get one in the case of any family. And that's more or less expected because basically you have L functions that trivially vanish at 1/2. Then the logs are minus infinity, and then of course the conjecture is not true. And basically for orthogonal type or odd types, we know there are not only like one sign in the functional equation, and if half of them is -1, then you have half of the L function that vanish, and of course you cannot get more than something like that. So that's one remark. We cannot get as good as the conjecture. And also, not every support gives a non-zero result. Some of them, even having a result towards low-lying zeros, don't give anything interesting, and I put on the right the minimal value from which these eta are positive. There may well be negative. You can just imagine L very small. Okay, in practice, that's what we know, so a bit, yeah. Yeah. Yes, it's the same. So you get the same density of non-vanishing than these eta. And in fact, we'll see at the very end that it comes from basically the same argument. If the L value is negative, right? Ah, yes. Well, then, so basically in the, so that's something that's different compared to low-lying zeros, is that in the Keating-Snaith paper and conjecture, there's not something that clear about the families considered, but basically they're kind of doing as if it doesn't happen. So the reasonable family I defined are basically not all the modular form for which we know that there are a whole bunch of -1 in the functional equation. So of course, it doesn't make more sense in general said like that, but family by family, then we can know whether or not we can make the machine work. And in practice, here are a small selection of the literature of what exists in low-lying zeros, and I'll be discussing one of them. Well, I won't spend much time on that. I just ordered them so that we have like more GL1 families first, then a bunch of GL2 families, then some higher ranks, then some GSP4 families. So we know all that in different aspects by different people. They have all the possible kind of symmetries, say. They're all restricted. All these results afford only a certain kind of concentration for phi, and are not as strong as the density conjecture. And basically, they give a specific eta, thanks to this support. At least by what I'm explaining today, we expect that we can deduce indeed these eta, but we'll see that it's still a lot of work. Okay, and we'll be focusing on the case of modular form, which is well, the first, one of the most important cases that sparked all this literature due to Ivaniak, Liu, and Sornak in the level aspect. And in fact, that has been recently improved by Baluyo, Shendi, and Li up to support 4. And that would give a certain eta, and that's indeed what we got with Cha-Cha. So here's the proper statement. So we take a basis of new forms of the modular forms, K level Q, positive sign. And I just look at all the levels up to Q. And in that case, assuming the generalized Riemann hypothesis for the sim square L function, I'll pinpoint where that is used. Then we have the results indeed. So when Q grows to infinity, then we have this eta equals to 13/16 towards the normal distribution. And we have an explicit mean, which is half of log log of the conductor. Of course, here you can say it's half of log log of Q. Both are true. And a variance, which is also log log of the conductor. And that's what I want to explain today. How do we get these results specifically? And but you can keep thinking about, okay, these tools and the mechanics behind that seem to be pretty general and may work for various other families. Okay, just one thing here. I said in a smooth way, and all along everything will be smoothed. I will just write some of F or cardinalities as if they were sharp, but this is not true. So in fact, everything is smooth. So all my sums over F are in fact, well, this big sum, it's not that difficult. So it's the normal sum over the family, but smoothed only over the level. So just had a bump function phi, psi, and Q that kind of truncates Q less than Q smoothly. And then you have the natural Peterson weights that appear in the Peterson trace formula because you see it coming. It will be used in a trace formula setting. And it's an average, so I divide by the same sum of ones. Well, exactly that sum. Okay. So what's the strategy before entering into the detail of the arguments? We want to understand central values of a given L function. And that will be done, as I said, by using an explicit formula that I explain right after, and that basically expresses it in terms of three big terms. So one which is kind of trivial and transparent, and which will give the mean in the theorem. And then two other much more mysterious terms. One which is a sum of Fourier coefficients over primes, and another one which is a sum over zeros, basically what we never know how to really address in practice. So for now, we're reducing the problem to an even maybe harder problem. So the one on the left, of course, is already what appears in the theorem. So we're pretty happy we see the mean. Then the prime sum, the sum of coefficient will be harder to study, and we'll study it via the moment methods. So we'll understand how distributed they are by studying their powers so their moments, and that will give us that indeed it follows a normal distribution and makes the variance appear. And the sum over zeros, now we use the low-lying zeros results that we know by Ivaniak, Liu, and Sarnak in this case, and that's basically the only place where we see this connection, where we use the knowledge on low-lying zeros to deduce the knowledge on central values. And then that will be an error term for all but a certain number of forms that, like very small zeros, may exist, and these will make this quantity blow up. So we have to remove them, and that's the reason of the loss in the theorem, that we don't have density 1. So that's the sketch. And now I can cut the remaining half an hour in 3 times 10 minutes and try to explain the 3 columns. Well, the first one will be pretty quick. Okay, so let's start explaining this formula that splits the central L value in terms of coefficients, zeros, and other terms. So the explicit formula gives this relation between values and coefficient, and here it is. That looks like it. So let's on the left, you have the L value you're interested in, or its logarithm, so that's exactly the quantity you want to study. Then you have a sum over prime of Fourier coefficient, which more specifically, it's this one. In fact, P shouldn't divide the level, so you should add P doesn't divide Q there. But basically a sum of Fourier coefficient with some weights. And then you have the mean that we saw in the theorem, and then you have an error term, or expectedly an error term, which is a sum over zeros. And what you notice is that if the zero is very small, then everything blows up. And that's why controlling low-lying zeros is kind of well desired in this setting. But provided you know there are no small zeros, all that will be an error term, and then this term vanishes, but not so easy. Okay, you may notice, for those who know the strategies behind establishing these low-lying zeros result, that it's more or less the same. So for low-lying zeros, you write also an explicit formula for the one level density, and you have a sum of coefficient with different weights, and then remaining sum that you bound. And the connection may be seen also already at that level. Okay, how do we prove such a formula? That's a useful tool in practice, no matter the exact weight you have. It's a double computation of a vertical integral. So you look at the vertical integral of the log derivative, L prime over L, times certain weight, and you compute it in 2 ways. First way is that you can move the contour to the left. So you shift the contour to the left, and you pick poles. So you shift it to -infinity, say, and the x to the w will just disappear at -infinity. And you pick all the poles. So you have poles coming from vanishing of L. So you pick a sum over zeros of something. It's here. And you pick also a pole at 0 because of the W, and that's basically the L prime over L that appears here. So I put an arrow because, of course, you have logs and some extra details, but that's already part of what you see above. You have your logarithm that you'll get integrating these L prime over L, and the sum over 0. And on the other hand, you also can use the Euler product to say, oh, but we know that L is a product over prime, so you take its log and it's a sum over prime, and you can take a derivative and you get a sum over prime of what appears in the Euler product, and basically you see the spectral parameters that you relate to the Fourier coefficients in the Euler product. And that's the proof, exactly as the usual explicit formula for one-level densities. So will you? Huh? Yeah, sure. That's always the same. That was exactly in Selberg for zeta and for more general L functions. So that works generally. It's not new. It's just a reminder, so that it's not something that mysterious. It really comes from the structure of the L functions, and mostly Euler product and zeros. So as we said, we cut the central values in these three terms, and now we'll be studying the second one, sum over coefficients. And we'll be using something called the moment method, or we'll be interested in moments of this sum of coefficients. And I want to explain just a bit why we study moments. So remember, we want to study the distribution of the central value. So I can remove the expected mean, and then what remains from the explicit formula, if you remove the mean here, it's essentially the sum over coefficients plus error. So studying the distribution of the log L half minus the mean is the same thing as studying the distribution of P, my sum over coefficients. And that will be done by studying their moments. So I'll explain why right after giving the results. So that's the result we establish in that case for modular form, is that on average, the case moment looks like the case moment of the normal law. So why is that interesting? I proved that after. That's interesting to study moments. It may appear mysterious because, well, you can divide by square root of log x, okay? So that goes to the left-hand side, and you see the variance. And then you have that the case moment is exactly the case moment on the right. So provided you have the case moment that are equal, of course, you deduce that they're equal for any polynomial. And then you can approximate any function by a polynomial, L1 norm, and you can then approximate it by the bump function between alpha and beta. And now the left-hand side exactly tells you how many of these sum over primes are between alpha and beta. And if you remember, I should have written it on the blackboard, that's exactly the statement of the theorem. The number of forms so that the sum over primes is between alpha and beta is lower bounded by something. So provided you know very well what's on the right, typically the normal law, then you get your result. So it's sufficient to have a result like this one. And as I said, here you see the variance. You don't consider p to the k, but p divided by square root of log x to the k to establish the result. So it's sufficient to prove this boxed statement. And as I said, yes, I thought of putting it. So that justifies the conjecture. By the explicit formula, this is the sum over prime. And by what we just said, normalizing, this is the square root of log x that I will take to be the conductor. And conjecturally, that will be exactly the normal law, and the loss will come because it's not exactly p here, but there is this sum over zeros that we need to bound away. Okay, let's try to study now to prove this, to prove that statement. So remember, it's a sum over prime of Fourier coefficients. I take that to the power k, so that's just sum of bunch of coefficients. And I can package them together by conspiring primes. When the primes are the same, you can have squares or cubes, etc. So I can just package that so that the primes are different. And then, well, I may have any kind of powers, 1 to k. Of course, it can appear, but I will study differently depending on the power. And by induction, in fact, it will be sufficient to understand finally one of them. And of course, if you understand all of these by Cauchying and Hildering, you can reduce that. So that's an idea. So that's a strategy used very recently by Stephen Miller and students in August, in fact. They were studying moments of one-level densities, and they did exactly that. They study moments, they put to the k, they don't have the same weights, but they study them by packaging power by power. The induction is a bit fine, it's not so trivial. So I did add a slide in between, but apparently I may not have sent the right version to explain that induction. So yeah, the induction is kind of works by adding back the primes pi equals to pj and removing them. But by doing that, by removing them, you remove primes. So when you remove this condition, it's just a product you can separate. Then you can use induction, easy. And when you add them back, you're colliding two primes in a single one and putting a higher power. So then the induction will work because you'll have less factors. That's the spirit of the induction. Okay, so we need to study this sum over powers here for three kinds of powers: large powers, then two, and then one, that will work pretty differently. So large power will be pretty easy. We can bound directly, pretty roughly. So we use the link bound, which is uniform in F. And so any power is uniformly bounded, and the sum over prime, since the power is larger than 3, converges. So we can just bound everything by 1, everything converges, and that's in particular negligible in front of the main term. Okay. Easy, no need to spend more time on that, but note that that works so long as you have an alpha, a bound here towards Ramanujan with theta less than 1/2. So we know that for GLN, but we don't know functorality for all L function. And typically that's something I had in mind, kind of dealing with that too. For the standard L function for GSP4, we just don't know that, and that already breaks for the large bounds. Anyway, so the two hard parts are second moment and first moment, powers 2 and powers 1. So the second moments, they will contribute to the main term. They will give the variance, in fact. They will give this log x to the k over 2. And that's the statement. So the sum, remember that is just coefficient squared divided by p, is log x plus an error term smaller. Remember, x is of size conductor. And this statement, before proving it, already gives everything that was in the moment statement. It gives the variance, because when I expanded my p to the k, I picked a lot of these terms. So when we take to the power k, you can take k over 2 powers 2, and you get here your k over 2. And of course, if you pick less powers 2, you will have just a smaller power, and that goes in the error term. So the largest contribution of all the moments will be those for which you pick only primes 2 by 2, and that will give that size. And how many ways do you have to pack together powers when you expand 2 by 2? Well, there are that many. So you have to choose k over 2 of your primes, and to pair them 1 by 1 with the k over 2 remaining primes, for which you have factorial k over 2 choices. But then you're counting a bit too much because you could have swapped them. You're counting twice every prime, so you just divide by the number of swaps. So that's that quantity. Why not? And that quantity is exactly the case moment of the normal loop. So that's where it comes from, like a combinatoric way of getting the large terms. And so the variance was coming from that main term, and the distribution is just coming by the number of terms contributing that much. Okay, let's prove that now. So I'm giving like a box proof for this statement. So basically, we want to estimate that sum over primes, not dividing the level, of coefficient squared over p. I hope it's not too small. Well, we can do various things to massage that in order for it to be manageable. So we can add back the p dividing q, then just to have a complete sum, and that contributes pretty smallly. The sum of 1 over p is log x, and p divided q brings you an extra log q, number of divisors. Then you relate these a squared to the coefficient at p squared by the Hecker relations. We know that the coefficient at p squared is the coefficient of p squared plus 1. That plus 1 gives you a plus in the sum, plus of sum of 1 over p, and by Mertens estimate, that's the log x appearing as the main term. That's the only contributing part. And this is also something very similar to the low-lying zero setting, is that the main term always comes from this kind of trivial or easy discrepancy in the Hecker relations. Because Fourier coefficients are, say, easy, well, we expect them to have a lot of cancellation, so they will be always small. And only the difference between the quantity you have and the Fourier coefficients really matter in terms of size. And the type of symmetry of families also come from the exact shape of the Hecker relations. Okay, so then you can add the higher powers of P so that you get something that looks like a log of an L function. That's, of course, sum of 1 over P squared and more converge, so that doesn't harm. And then you can relate that by the Perron formula to a vertical integral of, this looks like the coefficient of the log of L of the sim square F. And then you can move the contour to the left. Yeah. And moving the contour to the left, you pick basically the pole at W equals to 0, and that's the logarithm of the symmetric square at 1. And that's where we bound it by log, log, log of the conductor. But here I use an argument by Cogdell, Michel, and Granville Sound, and they do use pretty good bounds to shift the contours. And basically the idea is to write this log as a very, very short sum with log terms. And to do that, you need to have pretty good zero-free regions. You can do a bit weaker than GRH, but basically a rectangle without zeros inside the critical string. And that's it. That gives the proof. You have your main term, and every other contribution is small enough. So these were the second moments, and that gives the main term in the theorem. Now what about the first moment? Alpha equals to 1. So first moment are the last one to have studied all the moments. The first moment, we'll use trace formulas. So here, for now, we never exploited any results on average over the family. So the trace formulas relate coefficients, sum over coefficients, that's exactly what we have, to other objects, arithmetic or geometric, and they look like that. Keshav mentioned Peterson yesterday. So Peterson and Kuznetsov, they look like these. So a sum over a coefficient with a certain weight that depends on mass or Peterson or Eisenstein is a delta symbol. That's the related topic. And a sum of Klosterman sums times another transform that depends on mass or Peterson. And so spectral and arithmetic side. So for modular form and the specific age, you will find the Bessel, the standard Bessel L function, and basically a constant. It's the Peterson trace formula. And for mass form and Eisenstein series, you leave the test function general, and you get the Kuznetsov trace formula. And we'll use both. That's why I'm recalling them. Okay, so the result I want to prove is that powers 1 don't contribute to the main results. We already have our moments, so we want to show, on average this time, that this is small. And that's something inspired by the work of Baluyo-Chendi Lee that I mentioned earlier, that proved the best result for low-lying zeros for modular forms. And we exploit a lot sum over families. So let's see how it works. Also sketchy proof. So we have a sum of coefficients. I get rid of the weights, but they are here. We sum coefficients. In fact, all along, we sum only on new forms, forms not coming from lower levels. So the first thing I need to do to use trace formulas, because trace formulas see the whole spectrum, so you need to add the whole automorphic forms, even from lower level, is that you add them. And that can be done by kind of Möbius inversion. That's an arithmetic sieving. And this is something already done in Ivaniak, Liu, and Sarnak. You add the old forms, you remove the multiplicities, and so you can write one in function of the other times the sum of Möbius functions and divisor functions. So that's explicit. Then you have a sum of coefficients, so you can use Peterson formula. So that's A of P times A of 1, which is 1, we don't see it. So the delta symbol disappears, and only remains the sum of Klosterman sum. Then what happens is that in front of that, there is the sum coming from the arithmetic sieving, with a lot of Möbius function, divisor functions, etc. And there's also the smooth sum, because I'm averaging over the family, as I told you, in this sum, there is a sum of a bump function of the level, etc. So that's in front of this Peterson trace formula. So now what I do is that I massage a bit, putting all back together. All these hidden sum in front and all this sum from the arithmetic sieving, I swap summation, and that changes a bit. It's not anymore a Bessel function, but that will be a sum of a lot of things depending on the Bessel function, another function. And because here you have a lot of divisors of lower level, that changes also the level you will be seeing here. And in fact, it lowers the level. So, okay, why not? But now this looks like very much the geometric side of the Kuznetsov trace formula. And by the Kuznetsov trace formula, you're writing your original sum over modulo 4 as a sum over the whole spectrum, modulo like mass forms and Eisenstein series, but of a lower level. And thanks to that, with everything explicit, so H is explicit, etc., and has pretty good, Fourier transform has pretty good decay, and then it remains to bound that. And here there's no, it's pretty lengthy, but there's no hidden or new trick. So for the discrete part, you can bound using spectral large sieve or bounds towards Ramanujan, the Ling. And for the continuous part, you can use Matt Young's work on making everything explicit. Fourier coefficients are explicit, cusps are explicit, etc. And you can just bound everything pretty roughly. And that's enough. That gives you something that is of essentially constant size with all the parameters in front. So we get our result where large powers don't contribute, powers 1 don't contribute, and only the second moment will bring you this log-log, and you get the distribution and the variance thanks to that. So we already have our statement, provided the big O term is indeed a big O nicely behaved term, so it remains to bound the sum over zeros. So recall it, that was what the sum over zero appearing in the explicit formula, essentially sum of something that looks 1 over gamma squared. And the problem is that, as I said, if gamma is very small, size very small, like 1 over log 1 over log x squared, then you already have a term which eats up the main term, and everything's lost. So that may happen. We cannot say it doesn't happen, but we may say maybe there are not so many forms, and that's what we will say. So that's the statement we will prove. The number of our forms such that this is the condition in the theorem, so such that that's what we're counting, the number of forms so that L value at 1/2 minus the mean divided by the variance is in alpha beta, so this is not a word quantity, but such that the error term is indeed an error term, is at least 13 over 16 of the whole family. And that's the 13 over 16 that appears in the theorem. We just throw away the others. Okay, so to prove that, we need to prove, to understand the relation between low-lying zeros, that's the one level density, and my sum over coefficients. So remember that we proved that on average, the moment is of that size. That's what we just proved in the previous section. And on average, that's the low-lying zero that we assumed, like Iwaniak-Lewis-Arnach. On average, the one level density is explicit, has an explicit distribution. Well, in fact, they are uncorrelated. So you can average that, and on average, the moment times the one level density will be equal also to the product of the average sizes. So the moment looks like that, and the one level density looks like that. So that's exactly saying they're uncorrelated. And that's not obvious at all, because of course, they are both of the same form, F. So there's no reason these really work. So that's asymptotically uncorrelated. Okay, how do we prove that? And how will we use that to prove our result? So to prove that, basically we use an explicit formula for the one level density. Same kind of proof as before, you integrate L prime over L times suitable phi function. And you get something like that in the one level density. You always get, well, always, in that case, the expected limiting behavior, the low-lying zero result, plus sum of coefficients. And the hard ones are only for P, not higher powers. Well, then, of course, this is constant. So you can plug that in there. That's a constant. And then the sum is already the previous result. And you get, and you can take it out. So that's the previous result. And that's the constant I plugged in here. So you already have the result with the easy term. And then you just need to, well, say that the remaining part is small. but the remaining part is essentially a coefficient. And what I just did before is to estimate a sum of product of coefficients. So adding one only changes the weight, but since I'm summing over the family first, we don't care. So it's exactly the same induction as before. Well, same, except that you have to say that everything still behaves correctly. But that's exactly the same argument. We already did the job. So that proves these uncorrelation results between moment and one level density. And now that's more or less the last math slide. How do we use that to show that the sum over zeros is small? So I hope it's not too kind of formally heavy, but it will be a bit long. So I wrote D is the one level density. It's the sum over zeros. Phi is the smooth function. I just don't write the argument. And what I write as sum over alpha beta just means sum over the F such that the quantity we want is between alpha beta. Log of L1/2 minus the mean divided by the variance square rooted is between alpha beta. And what we want to count using that is the number of small zeros. So let's cut this sum between in two. Those having small zeros, two small zeros so that the error term is bad, and those don't having small zeros. No deep math there. Now, since we can choose a specific test function, we can choose it to be 0 at 1. And since the zeros are small, they're close to 0, so the value of h at these zeros is close to 1. I won't write the epsilons, but basically each two small zero here contribute by a 1 because they are small. So here I can lower bound by 2 minus epsilon, of course not a 2 minus epsilon. And then I can just complete the sum. So I can just complete the sum here by adding those that don't exist and removing them here. I don't do anything specific. And now D, remember that D is the sum of that function. And my test function, I can take something positive, basically the Fächer kernel. I will take something positive, so I can just bound from above that 2 minus D by 2. D is positive. And remember, this is the kind of thing that I want to lower bound. That's the number of good terms. If there are no small zeros, then the error term behaves well. So if I have a good lower bound on that, I'm done. That's what I want. So I can lower bound it a bit artificially by that because I know information about that. And then I replace. This is lower bounded by the sum over phi twice minus this sum. And now I can use the results that I established before. Because what is that? This is the number of terms for which my quantity is between alpha beta, but that's exactly what the moment method gives. And this is the same thing times the one level density, but we just said that they're uncorrelated. So let's write it. By the moment method consequence, the number of forms with the quantity between alpha beta is given by this m alpha beta is just the integral between alpha beta of the normal low. So that's the normal low integral, and I remove the condition. That's the proportion. And then for the other sum, I said it's uncorrelated. So this is the limiting one level density times the number. The limiting one level density is the integral of phi times w, of h times w. But h is explicit. I just pick one, and w is explicit. It's one of the 5 types, and I can compute it, and it's 3/8. And then this sum, same as above, it's just the normal low distribution. So I get my 3/8. And so here I get 2 minus 3/8, and all that halves, and I get the result. So the number of good terms is at least 13 over 16. And that gives you then, thanks to the low-lying zero result, the uncorrelation lemma, and still the moment, because I said we'll repeat more or less the same proof, that there are few bad gammas, few bad small zeros, and these just gives you the 13 over 16 proportion. So that gives the proof of the theorem. Everything is as expected. And just conclusion, kind of on time. So what did we learn? That's what we understood doing all that. We started trying to understand the Sound and Radziwill paper to understand where the low-lying zero entered into account. Then we noticed that everything had to be reproven because it was a bit twisted, but the tools were pretty accessible. So basically, we need bounds on spectral parameter and Hecker relations, which we know in many cases. We know quasi-orthogonality statements, trace formulas, and being able to use them. And we need a limited one-level density statement, which basically follows from the three first ones. And so, okay, it remains to do that on the other cases. We have all these tools and basically the table I gave in the beginning with other low-lying zero statements. So I hope it gave some ideas for well, the problem session of tomorrow, and that was what I was willing to say. Thank you.
Thank you very much. Does anyone have any questions for Didier? Yeah.
Hello. Okay, so the first and the third moment in the end didn't contribute anything but error.
Exactly.
Like, should I view that as the same statement that the odd moments of the normal distribution vanish? Is that related?
No, because in the large moment, you also have even moments.
Ah, okay.
You have everything larger than 3.
Got it. Thank you.
But indeed, it may be stated, for the odd ones, it may be stated, but they don't vanish. They just contribute in a more negligible manner than this log x. So yeah, it's not that strong. There's one behind you.
Ah.
So one question was, you slightly use the average over the level, like Balliot, Phi and Shan. So I was wondering whether, what was the reason to do that? Did you need it to get?
So in fact, yes, that's, so maybe it can be removed, but in practice what happened, so what I hid a bit under the carpet was using this trace formula, there is this reciprocity strategy where you write Peterson, you massage a bit, that's a Kuznetsov, and you bound away. But in doing that, this smooth function enters into account, into the new function appearing on the right side of Kuznetsov. And that decays a lot. And the pre-transform will decay a lot, and that helps in bounding, in pruning the sums and bounding what remains. So it's not obvious, it may be doable. I have no reason to say it couldn't be removed, but in the method as written, we make a lot of use of this decay.
Okay, the other question I had was, when you give a description of the proof strategies, so the bit in the middle where you're computing the moments, that's the same as the one-level density argument in general, right? Where you're computing the moments of the prime sums.
Yes.
That's exactly what shows up when you're doing one-level density.
Exactly.
Family, right?
And even if you go even earlier in the proofs of all that, what I said at some point is that all that comes from Hecker relations. Because indeed, as soon as you have Fourier coefficients, basically you say, oh, but all that is small because there are a lot of consolation, provided you know how to prove it. And the only thing that really remains, and that's what motivates the conjectures, is that in the Hecker relations, you have some constant terms, and these will contribute, and you already see that at that point, before Peterson, before averaging, etc. Even one by one, you see this contribution. But yeah, it's the same. It's exactly the same reason as for the low-lying zeros.
Thank you.
Any further questions? Yeah.
So what happens if you estimate the second moment also using trace formula? I mean, why do you need to go to?
So, well, then you'll have a main term because then you estimate AP times AP. So you can, probably it will be easier for all the remaining terms because you have a higher power in the denominator. But then you have the delta n equals to m. It was 0 in that case because I was estimating AP times A1. But for second moment, it will be AP times AP. And this delta, this particular delta symbol probably gives you just a constant that will be a sum of 1 over p's, and that's the log. That's my easy guess, but it should work like that. At least the main, so yeah, maybe both could be just done in the exactly the same framework.
Then you don't have to use GRH, right?
You're right. It may be true. Okay, we don't have to use GRH. It may be true, said like that. Well, in that case, we don't need to use GRH for the main term. We need to use GRH for what remains. So it may be that in this application, you still have the same issue, even for the delta equals 1, like just for the delta term. So it may be exactly the same problem, but it's a good point.
Any final questions? Yeah.
Hi. I just wanted to ask, so when you're talking about like lower bounding the number of forms in a family for which the central value, like properly normalized, is in a certain interval, one aspect of that is that you could ask for how many forms is this central value, for example, very small, right?
That's right.
Okay, and so you're saying you're giving a lower bound on
yeah.
that, right? And right now, the way your statements are formulated is somehow what very small means is like whatever, there would be like a constant, right?
Yeah.
But my question is, have you tried, or is there any hope of pushing these alpha and beta to grow a bit with the size of the family?
I see. Okay, I see. To have to really like
So
finally estimate the number.
To find super duper small values.
I haven't tried it. That's a good question. But indeed, that's probably worth it, because at least the method really sparked interest towards these questions, because we see that these are those that are really harmful. And so maybe knowing those that are almost of constant size could also help to have just a middle range that may also improve. But I haven't tried it.
Okay, perhaps we'll leave it at there. We're going to start again in a few minutes, but let's thank Didier again for an excellent talk.
Thank you.